The MiG-21's most iconic feature, its nose intake, was also its Achilles heel. It constrained radar size, and in air combat, that means finding and fixing targets suffered at range. Israel didn't guess that. It tested it, thanks to an Iraqi defection. We'll put that intake against the Delta Wing's climb advantage, then show how short endurance, about 45 minutes in combat load, shaped predictable tactics. Stick around to see how those constraints became a playbook. Drag the fish bed into fuel anxiety, deny it long-range cues, and force it to fight on a clock. Before we move on, please take a moment to subscribe to the channel and like the video. What if the same wing that let the MiG-21 climb like a rocket also forced it to leave the fight just as it found it? Soviet designers selected a compact Delta because it solved multiple constraints at once. The planform tolerated high Mach numbers without complex sweep mechanisms, and the structure handled high angles of attack without fragile hinge lines. You got strong torsional stiffness, fewer moving parts, and a small airframe that could live on rough fields. It was therefore a rational interceptor choice. Short takeoff, steep climb, and a small radar cross-section from a tight planform. But the Delta charged fees in the regime where most fights actually unfold. Induced drag soared at lower speeds because a slender Delta needs high lift coefficients to turn hard, and that means energy bleeds quickly. The wing's internal volume also stays thin, so fuel sits mostly in the fuselage and roots, which caps endurance. Higher landing speeds and long takeoff runs followed from that same geometry, so you burned fuel to get airborne and then burned more to maneuver. If you sum all of that up, a typical combat load put the fishbed airborne for roughly 3/4 of an hour, and real intercept profiles trimmed that further. Scramble, climb, brief radar cueing, one pass. The doctrine fit the airframe. It did not like waiting, dragging, or resetting after a merge. A protracted turn fight meant sustained high angle of attack, which meant drag, which meant minutes disappearing from the clock. By way of example, an interceptor launch that arrives slightly early forces a shallow hold with periodic corrections. Each correction costs speed, and you buy it back with throttle. That trade repeats through the merge, so the fuel margin that looked safe on rollout evaporates once the jet is asked to turn and climb twice. Think of it like a sprint car tuned for quarter-mile bursts, not a touring car built to loiter and reposition. It goes fast in a straight line and it gets to altitude fast, but it punishes any request to stay and fight in the subsonic band where induced drag dominates. Israeli testing took that endurance math and turned it into a lever. They stretched fights vertically, then laterally, and forced the Delta to pay drag penalties on every pull. One way or another, that produced early bingo calls. The wing that won the height war lost the time war. We can now move on to the feature that set the entire nose profile and set hard limits on what the pilot could see electronically. Why did the MiG-21's biggest intake also shrink its eyes? The single large nose intake solved the airflow problem cleanly. Air came straight in. The shock cone set the supersonic boundary, and the duct stayed short. That cut weight and drag, and it let the airframe stay compact without the plumbing and doors you see on side inlet fighters. It was therefore a quick path to Mach numbers the program wanted, with fewer failure points for a conscript force to maintain. But the same shock cone and ducting boxed the radar into a narrow ring around the cone. Antenna diameter drives gain, and gain drives usable range and resolution. When the space available is an annulus measured by the distance from cone to duct wall, you start small and you stay small. There is no growth room without moving the intake off the nose, so every later set inherits that aperture limit. Early RP-21 and later RP-22 installations reflected that geometry. Power helped, but the antenna face remained constrained by the intake throat. Smaller dishes lose sensitivity, and look-up versus look-down suffers as ground clutter raises the noise floor. So you might hold a lock on a clean target at medium range, but the moment you add terrain return or maneuvering, the solution degrades. Operationally, that shaped behavior. In Vietnam and across the Middle East, MiG-21 flights leaned on ground control intercepts for the initial vector and timing. When those datums broke, jamming, terrain masking, or simple latency, awareness dropped fast because the onboard radar could not build a wide, stable picture on its own. The consequence was a narrow window to acquire visually and commit. Operation Diamond removed guesswork. With a flyable Iraqi MiG-21 in hand, Israeli teams measured practical lock ranges and mapped where the radar struggled in clutter and maneuver. That testing aligned tactics with physics. Deny clean GCI vectors, force altitude and aspect changes, and the radar's small aperture works against the pilot. Think of it like using a flashlight with a narrow lens. It throws a tight beam, but it cannot flood the room. If the beam misses, you hunt by feel. By this point, if the radar could be denied, the pilot was left managing timing and energy under a high workload, with a tight cockpit and limited forward view over the nose in high alpha. The intake bought the speed but sold the radar, and Israeli playbooks cashed that trade by creating visual merges on their terms. With limited sensors, the engine had to carry the fight. Let's see what the Tumansky could deliver, and what it cost. The MiG-21 could climb hard on afterburner, but every second on burner was a debt it had to pay back at the tanker that never came. Tumansky's compact cores delivered the numbers that made the airframe viable as an interceptor. Early R-11 F2-300 installations produced roughly 39 kilopascals dry and about 57 kilopascals in afterburner, which gave brisk acceleration and a steep initial climb. Later, the R-25-300 raised that to around 40 kilonewtons dry and nearly 70 kilonewtons in reheat, so the thrust-to-weight improved, and the jet leapt uphill faster. It was therefore excellent for short-field scrambles and for reaching altitude on schedule. But the meter ran fast. Afterburner multiplies fuel flow while the MiG-21's tanks remain small, so every vertical pull or draggy turn burned minutes off a mission clock that started near 45. Energy dominance was a brief privilege. Misjudge a merge or overshoot once, and the reserve that looked fine in the climb became a recovery problem. In practical terms, acceleration profiles looked sharp at low to medium altitude with burner lit, then tapered as speed rose and the intake geometry stabilized. You could trade altitude for airspeed quickly, and the airplane responded crisply, but each exchange came with a fuel penalty. A pilot who stayed in burner through a sustained vertical would see the clock collapse, so intercept standards emphasized clean, timed runs rather than dogfights. That drove operational caution. Combat air patrols or chases beyond a few turns were risky because the consumption curve bent steeply upward under high G loads. The standard move remained a controlled intercept. Take the cue, climb, commit, fire, and exit. When that script broke, the MiG-21's margin disappeared. Israeli training after Operation Diamond leaned into this. They pulled fish beds into high G turns and repeated verticals, where induced drag and burner demand compounded. One way or another, that forced early fuel calls and degraded options on the next merge. Upgrades later, BIS airframes and Bison refits, added better radars, new weapons, and cockpit improvements. But none of that reshaped the fuel volume or intake burner relationship. The constraint held. By this point, the Delta's drag curve, the intake's limits, and the compact engine's thirst converged into a predictable envelope. Israel didn't need to outrun the MiG-21 all day. It only needed to make it run out of day. The parts add up to doctrine. Here's how those trade-offs shaped a repeatable way to win. How do you turn a captured jet into a checklist to beat it? Operation Diamond produced a flyable MiG-21, so test teams could isolate variables rather than guess from combat reports. They logged sensor behavior with controlled targets at set altitudes, then repeated runs with different closure rates. They recorded cockpit workload during high alpha pulls and noted how the sightline over the nose changed with pitch. It was therefore a complete data sweep. Performance curves, sensor limits, and pilot ergonomics tied to repeatable test points. Structured evaluations produced if-then logic that aircrews could brief in minutes. If the MiG entered hot and high with GCI support, then force an altitude change and deny the vector. Its radar struggles during aspect shifts. If it stayed to turn, pull it through sustained high G where induced drag and burner demand stack. The fuel clock moves faster than the picture updates. If it chose the vertical twice, reset laterally and make it pay for the second pull with range. The tactics that emerged prioritized timing. Deny the data link queue by dragging through terrain and altitude blocks. Create a visual merge on favorable geometry, then bleed energy with verticals and loaded turns. Pair tactics reinforce this. The lead fixed the MiG nose on to occupy its narrow radar and gunsight cone, while the wingman slid to an offset where a missile shot matured as the MiG traded energy for a fleeting position. One way or another, it faced a choice between energy and endurance, and neither recovered quickly. US programs later validated many of these behaviors in dissimilar air combat training, which aligned threat presentations and fuel state pressures to the same envelope.